from bridges cracking under pressure to collapsing in flames. These weren't unpredictable. They were preventable. You won't believe what's waiting at number 5. A critical U.S. bridge built with a fatal engineering flaw that experts had warned about for decades, but it was ignored to save money. And number 6? It's the deadliest collapse on this list. One moment the bridge was there, the next, a bus full of passengers drove straight into open air. When a ship crushed Baltimore's Key Bridge in 2024, one would have thought that we learned from that deadly 1980 bridge collapse. It is the latest in a disturbing pattern of U.S. infrastructure failures. Failures that engineers warned about and were ignored. We'll break down 7 real-world bridge disasters in the U.S., examine exactly why they failed, and expose the systemic cracks in engineering, inspections, and accountability that continue to put lives at risk. This is more than a list. It's a wake-up call. So how does one of the world's richest nations keep letting its bridges collapse? While China builds entire megastructures in weeks. The Francis Scott Key Bridge collapse, Baltimore, Maryland. It was just after 1:24 a.m. on March 26, 2024, when the container ship Dolly, a 948-foot-long cargo vessel, experienced a full electrical blackout while exiting the port of Baltimore. With no power and no propulsion, the massive ship veered off course and slammed into one of the main support piers of the Francis Scott Key Bridge. What followed was total structural failure. The bridge collapsed in a matter of seconds. Surveillance footage captured the horrifying moment as the structure folded into the Patapsco River like matchsticks. At the time of impact, a crew of 8 construction workers was repairing potholes on the bridge. Only 2 survived. The Key Bridge wasn't some minor overpass. It was a 1.6-mile steel continuous truss bridge that had served as a vital artery for over 45 years, connecting Baltimore's port traffic to the I-695 Beltway. Built in 1977, it handled roughly 11 million vehicles annually. But despite its size and importance, its defenses were tragically outdated. Unlike many bridges in busy shipping corridors, the Key Bridge's support piers lacked marine fender systems. Heavy-duty structures made of steel, concrete, or wood that surround piers and absorb the force of ship impacts. Ports like Tampa, New York, and San Francisco upgraded their bridges years ago. But in Baltimore, no such retrofit had been funded. This collapse wasn't an anomaly. It was the result of inaction, and one that cost 6 lives. Fern Hollow Bridge collapse, Pittsburgh, Pennsylvania. It was a quiet Friday morning in Pittsburgh when everything gave out. At 6:39 a.m. on January 28, 2022, the Fern Hollow Bridge, a 447-foot-long structure crossing over a wooded ravine in Frick Park, suddenly collapsed without warning. A city bus, 5 passenger vehicles, and thousands of pounds of steel and concrete plummeted nearly 100 feet into the valley below. 10 people were injured, including the bus driver and several passengers. The only thing that prevented fatalities was the timing. Rush hour hadn't yet peaked. The structure, opened in 1970, was a rigid steel frame bridge, a design that relies heavily on its legs and cross-bracing for stability. But by 2022, that same steel had been corroding for years. Inspection records showed the bridge had been rated poor as far back as 2011, and that rating remained unchanged for over a decade. The NTSB's final report revealed just how close this bridge had been to failure for years. Critical load-bearing legs were severely rusted, and some connection plates had deteriorated to the point of detachment. Water intrusion, poor drainage, and a lack of consistent non-destructive testing allowed the decay to continue unnoticed, or worse, ignored. What made the collapse especially damning is that the bridge had undergone routine inspections. It was last checked just 4 months before it failed. Yet without advanced tools like ultrasonic scanning or internal stress sensors, inspectors missed the most dangerous flaws. The bridge literally failed in its legs. These are the kinds of failures that can and should be caught. Jennifer Homendi, NTSB chair. This wasn't some unpredictable fluke. Engineers had raised concerns for years, but the warnings were met with silence. Hernando de Soto Bridge crack, Memphis, Tennessee. On May 11, 2021, a routine inspection of the Hernando de Soto Bridge over the Mississippi River revealed something terrifying. A massive, 2-foot-long crack in a key load-bearing member. The fracture was found in a steel tension tie girding the central arch, one of the critical elements holding up the entire 3,800-foot structure. This wasn't just a small oversight. It was a near disaster. The Hernando de Soto Bridge is a tied-arch bridge completed in 1973, carrying over 40,000 vehicles a day between Tennessee and Arkansas. The cracked component was a tension tie, a member that literally holds the arch in place under load. Had it failed completely, the result could have mirrored the I-35W collapse in Minneapolis, a full structural failure during peak traffic. The Tennessee Department of Transportation called it a near catastrophe. The NTSB later concluded that inadequate inspection procedures and human error were to blame. The event became a wake-up call. State DOTs across the country began rolling out drone-based inspections and AI-assisted crack detection to reduce human oversight failure. But the fact that such a large, obvious fracture went unnoticed for years revealed deep flaws in America's infrastructure monitoring. It wasn't luck that saved this bridge. It was timing. Had it gone unnoticed a few months longer, the outcome might have made headlines for all the wrong reasons. The Liberty Bridge fire, Pittsburgh, Pennsylvania. In September 2016, Pittsburgh came within inches of losing one of its oldest and most important crossings. The Liberty Bridge, a cantilever truss bridge built in 1928, spans the Monongahela River and funnels traffic directly into downtown Pittsburgh. It carries more than 50,000 vehicles daily. But on September 2nd, during a routine rehabilitation project, a small oversight nearly triggered disaster. While contractors were using acetylene torches to perform welding work, sparks ignited nearby plastic ventilation pipes. The fire spread rapidly, creating intense localized heat that deformed a key steel tension cord, one of the elements responsible for keeping the bridge's span stable under load. According to PennDOT, the temperature reached levels high enough to warp steel. The bridge was immediately closed and underwent emergency repairs. Engineers installed a 9-ton steel brace to stabilize the damaged section while assessments were made. The cost of the incident? Over $3 million in repairs, 24 days of emergency closure, and tens of thousands of daily traffic disruptions. But what's more concerning is what caused it. Poor job site controls. Flammable materials had been stored too close to active torching, and there were no thermal shields in place, a violation of standard safety protocols. The I-35W bridge collapse, Minneapolis, Minnesota. On August 1, 2007, just after 6 p.m., one of the busiest commuter bridges in Minnesota, the I-35W bridge over the Mississippi River, suddenly gave way. 8 lanes of rush-hour traffic fell into the river, along with construction workers, vehicles, and equipment. 13 people were killed. Another 145 were injured. It remains one of the deadliest bridge collapses in modern American history. At first, many assumed it was just another case of aging infrastructure. The bridge, after all, had been built in 1967 and was already 40 years old. But as investigators from the NTSB and independent engineering firms dug into the details, a much more unsettling truth emerged. The collapse was caused by a fatal design flaw. The gusset plates, flat steel connectors at key structural joints, were too thin. At just half an inch thick, they were half the recommended size for the loads the bridge was carrying. The structure was what engineers call fracture critical, meaning it had no redundancy. If one key component failed, there was no backup to transfer the load. The bridge didn't collapse because of a single event. It collapsed because of a silent accumulation of stress on a hidden flaw, a flaw that had existed since the day it was built. The disaster led to a national reevaluation of fracture-critical bridges. But it also exposed the cost of cutting corners in design and the dangers of ignoring warning signs until it's too late. Sunshine Skyway bridge collapse, Tampa Bay, Florida. On the morning of May 9, 1980, a sudden storm swept across Tampa Bay, reducing visibility to near zero. As the freighter Summit Venture made its final approach to the port of Tampa, it lost sight of the Sunshine Skyway bridge. Wind gusts exceeding 60 miles per hour pushed the ship off course. At 7:38 a.m., the freighter slammed into a bridge support pier at full speed. A 1,200-foot section of the bridge collapsed instantly. Moments later, a Greyhound bus and several cars unknowingly drove off the severed edge of the roadway and plummeted 150 feet into the water below. 35 people were killed. No one survived. The Sunshine Skyway, built in 1954, was a cantilever bridge, a design that relies on long horizontal beams anchored only at the ends. The pier that collapsed was unprotected. There were no reinforced barriers, no fendering system, and no advanced radar navigation tools to guide ships in low visibility. It was simply exposed. In the aftermath, public outrage was swift and massive. The entire bridge was demolished and a new one was built. A modern cable stay design, opened in 1987, featuring massive concrete fenders and improved ship detection systems. It became a textbook case in engineering circles for why maritime impact protection is essential. BNSF, rail trestle collapse, Tempe, Arizona. Just after 6 a.m. on July 29, 2020, a freight train rumbled across a wooden trestle bridge spanning Tempe Town Lake in Arizona. Moments later, the air filled with the sound of splintering timber and exploding metal. The bridge, a patchwork of steel and century-old wooden supports, was on fire. 10 cars derailed. 2 of them plunged into the lake. One tanker car, carrying hazardous chemicals, ignited and sent a plume of black smoke over the city. Nearby residents were told to stay indoors. Local officials declared a Level 2 hazmat emergency. The bridge itself had been built in 1912. That's not a typo. It was over 100 years old. While some portions had been reinforced with steel over the decades, much of its structure still relied on timber, a material especially vulnerable to heat, arson, and Arizona's extreme summer temperatures. Investigators with the NTSB and Tempe Fire Department were never able to conclusively determine whether the fire was caused by accident or arson. But the risk was always there, and well known. Modernization remained on the to-do list, until it was too late. The collapse forced a broader conversation across the freight industry. How many other 100-old structures are still quietly in service? And how many are one spark away from disaster? Outdated inspection methods, deferred maintenance, under-engineered designs, critical upgrades postponed over budget constraints. The warning signs were there, documented, photographed, reported. But time after time, action came too late. In some cases, like the Hernando de Soto crack, timing spared catastrophe. In others, like the Key Bridge or the Sunshine Skyway, lives were lost in moments that engineers had specifically predicted decades earlier. In the time it took the US to repair a single fracture in Memphis, China opened the 55-kilometer Hong Kong to Zhuhai-Macau Bridge, one of the longest sea crossings ever built. They're not just building faster, they're embedding smart sensors, using AI for real-time stress analysis, and enforcing stricter standards for maritime protection systems. The very kind the Key Bridge lacked. America leads the world in GDP. But in critical infrastructure, it's falling behind. So how many more warnings will be ignored in the future?